Welcome to the Deep Dive. Today we're plunging into a world that has seen, well, an absolutely dramatic transformation, yet often struggles with development methods that feel almost artisanal. I'm talking about FPGA development. Think about it. We've gone from wiring up simple logic gates to designing incredibly complex systems on chip, integrating processors, high-speed interfaces, huge blocks of IP.
It's really incredible how far the designs themselves have evolved.
Exactly. But so often, the traditional ways of developing them haven't quite kept pace. It can feel like we're trying to build, I don't know, a complex custom supercar with, like, hand tools. It feels like a fragile art sometimes.
That's a perfect analogy, actually. This growing complexity in FPGA designs has really put a spotlight on a critical vulnerability, the development environment itself.
Right.
If that foundation isn't perfectly stable, it just introduces huge risks, creates significant inefficiencies, and frankly, severely impacts the predictability of the entire process.
So our mission today is to explore exactly that. How Docker, the industry standard containerization platform, offers a strategic, almost revolutionary evolution for professional FPGA development, specifically with AMD's Vivado design suite. We're going to show you how Docker can stabilize that entire environment, offering you, our listener, a real shortcut to predictable and scalable FPGA design.
And our goal here is really to provide you with a thorough understanding of this complex problem. And it's rather elegant solution. We want to give you those aha moments, show how these systemic issues can be tackled with clever, practical approaches, ultimately saving you significant time and reducing a lot of frustration in your development cycles.
All right, let's unpack this then. Because before we dive into how Docker comes to the rescue, we need to truly understand the fundamental systemic problems that plague traditional Vivado workflows.
Yeah, you really do.
These aren't just minor annoyances, right? They're critical challenges that hit productivity, quality, project risk, right where it hurts.
Yeah.
We're talking core issues like reproducibility, version control, dependency management.
Indeed. And at the very core of any rigorous engineering discipline is that principle of reproducibility. You give the process the same inputs, you should get the same outputs every single time.
Right.
But with Vivado, this principle is, frankly, alarmingly fragile.
Alarmingly fragile. That's a strong phrase. What makes Vivado so uniquely susceptible? I mean, software compilers generally give you the same binary from the same source code. Why is hardware, or this hardware flow, different?
That's a great question, and it really gets to the heart of the why. Vivado's bitstream compilation, that final file you program onto the FPGA, is profoundly sensitive to the host environment it's running in. Unlike typical software compilation, which mostly interacts with, let's say, standardized OS APIs, FPGA toolchains like Vivado interact at a much lower, much more granular level. They're pushing against specific device drivers, specialized libraries, and even the nuances of how the operating system handles multiprocessing. It's almost like a delicate orchestra. We're just one out-of-tune instrument, like a minor OS patch, or the number of CPU cores available during the build, or even something as subtle as a system-level locale setting that introduces an unexpected character encoding. It can throw the entire performance off.
Wow.
Even AMD's own documentation acknowledges that Vivado results aren't guaranteed to be identical across different operating systems, like Linux versus Windows.
So it's not just the classic, it works on my machine. It's more like it works on my machine right now in this exact configuration with this exact number of CPU cores and this specific patch level and maybe the phase of the moon.
Exactly. It sounds like a recipe for constant soul-crushing headaches.
It absolutely leads to what we call the unpredictability tax. This is that hidden cost, right? Engineers spending valuable time debugging the tool chain and its environment instead of their actual design logic.
Imagine a critical build failing with a cryptic no error message. Or worse, silently generating an incorrect bitstream because it used some outdated cache module without warning you.
Oh, no.
That's engineering time and creativity just redirected away from value-added work, often late at night, trying to figure out why the tool broke.
And I've heard this can lead to what people call upgrade paralysis, where teams just get stuck on older Vivado versions.
Yeah.
Have you seen teams become genuinely, paralyzed, just abandoning upgrades for fear of breaking something?
Oh, without a doubt. Teams become justifiably fearful of modifying a working environment. Upgrading the host OS, applying security patches, even moving to a newer Vivado version becomes this high-risk activity.
Like playing Russian roulette with deadlines.
Exactly. It's perceived that way, and this locks them into older, potentially buggier tool versions, preventing them from benefiting from new features, performance improvements, critical bug fixes. The development environment, which should be a stable foundation, instead becomes this source of risk and anxiety.
That really highlights how the "it works on my machine" problem is particularly acute and costly in FPGA development. So if reproducibility is a crisis and we're stuck in upgrade paralysis, what's the next domino to fall? Ah, yes, dependency hell coupled with that version control dilemma.
You've hit on it. The way Vivado handles projects has profound implications for version control, especially with something like Git. Vivado offers two main flows: project mode and non-project mode.
Okay, project mode, it has that familiar GUI, wizard-driven flow. Seems user-friendly on the surface, but you mentioned it's a nightmare for version control. What's going on under the hood there?
Well, it's not just messy, it's almost an anti-pattern by modern software engineering standards. Project mode creates this sprawling, complex directory structure right there on your disk.
Right.
And this isn't just your source code, it's filled with hundreds of megabytes of binary files, intermediate build products, configuration files, and they often contain absolute paths hard-coded into them.
Absolute paths. Oh dear.
Yeah. Trying to commit that directly to Git is just impractical. Binary files are difficult to merge, they bloat the repository, making cloning glacially slow, and those absolute paths break instantly if you move the project or even just change user directories. It feels like it was designed for a single workstation, not a collaborative, version-controlled team environment.
So even those workarounds like Right Project Tasted Show, they feel like clumsy attempts to fit a square peg in a round hole.
Exactly. They require complex, often error-prone procedures just to avoid losing work or creating massive merge conflicts. It's not clean.
Okay, so contrast that with non-project mode.
Non-project mode. It's almost universally praised by experts. This flow is entirely driven by tool command language scripts, TCL.
TCL, right.
Vivado operates basically on an in-memory project.
Yeah.
It reads your source files and executes the entire synthesis to bitstream flow based on a sequence of TCL commands you provide. Critically, nothing is written to disk unless you explicitly command it to write something.
That sounds like a total game changer for version control. Now your entire build process is defined in human-readable, text-based TCL scripts. Easy to version, easy to diff, easy to merge.
Exactly. This is what modern software teams thrive on. It's a natural fit for Git.
But here's the catch, right? The vicious cycle you mentioned.
Precisely. Even with the superior non-project mode, its reliability is fundamentally undermined by that fragile host environment we just discussed. A team might meticulously create a clean, scriptable non-project workflow, only to have its reliability torpedoed by a minor OS update on one developer's machine, or a subtle difference in locale settings causing a TCL script to fail.
So they solve the version control problem.
Only to be immediately confronted head-on by environment sensitivity. It's just a clear demonstration of the absolute necessity of stabilizing the entire ecosystem, not just parts of it.
Anyone who's wrestled with versioning complex software knows this pain, but for hardware, where bit-for-bit reproducibility can literally be a legal or contractual requirement, it becomes an existential threat. Underscores the need for that stable foundation.
Absolutely.
Which, perhaps counterintuitively, brings us to the third big challenge.
Yeah.
Dependency hell.
Yeah, FPGA projects often have very long life cycles. We're talking multiple years, sometimes spanning multiple Vivado versions. This presents a huge logistical burden.
Right.
Teams frequently need to maintain several Vivado versions simultaneously on their systems. Each one takes up, over 100 gigabytes of disk space.
Wow.
And just installing multiple versions side by side can lead to conflicts with system environment variables, potentially causing one version to break another. It's messy.
And upgrading an existing project.
Yeah.
Sounds like it's not just time-consuming, but notoriously hazardous.
It's rarely just a simple recompile, unfortunately. A new tool version might change constraint syntax, it could invalidate old TCL scripts, or require a really complex manual upgrade process for all the IP cores within the design. It's kind of like having to rebuild your entire car engine just because you want to install a new GPS system.
That's a great analogy. And even within a single project, a single tool version, Vivado's internal dependency management can be surprisingly unreliable sometimes.
Yes, I've heard reports and seen issues where the tool fails to detect source file changes, leading to stale cached modules being used in the build.
Violently.
Sometimes silently, yes. Or the IP packager might fail to update revision numbers correctly. And remember that specific TCL85T.dl issue in Vivado 2024.1 that required a manual patch from AMD just to make certain TCL commands work again.
Right, I remember that. These aren't trivial things.
No. And these challenges point to a more profound need than just managing source code. They really highlight the need to version and archive the entire build environment associated with a specific project release.
The whole environment.
The whole environment. And this is precisely where Docker image comes in. It serves exactly that purpose. An immutable, self-contained snapshot of that entire environment. Imagine pulling my company Vivado.2021.2 Project Alpha and knowing with absolute certainty that you have the exact toolchain, libraries, everything used for that specific build.
That changes things.
It transforms the container from just a development convenience into a long-term strategic asset, especially for regulated industries, aerospace, medical, automotive, where bit-for-bit reproducibility and audit trails are mandatory.
So for anyone who's struggled with software dependencies or legacy systems, this applies that pain to a whole new level in hardware. But okay, we've spent enough time wallowing in the problem space. Let's turn to the solution, because this is where Docker really shines, right, in addressing these challenges head on.
Absolutely. Docker's core principles, encapsulation, portability, and efficiency are direct, elegant answers to the fundamental problems we've just outlined.
Okay, let's start with encapsulation and isolation. The self-contained toolchain idea. What does that specifically mean for taming something like Vivado?
It means Docker can bundle the entire Vivado application, all its binaries, all its required system libraries like glip, critical runtimes like TCL, and all the necessary configuration files into a single isolated package, the container image.
And this container then runs in its own little world.
Exactly. Completely separated from the host OS and any other software on your machine.
And that isolation is the direct antidote to environment sensitivity, right?
Right.
Because issues like host OS patch levels or conflicting libraries, they just become irrelevant.
Precisely. The Vivado toolchain inside the container is completely insulated from the host. Its behavior is determined solely by the contents of that container image, not the unpredictable vagaries of the machine it happens to be running on. This delivers a perfectly controlled, deterministic environment. It's like black boxing. The entire development setup ensures consistency every single time.
Which naturally leads us to portability and consistency, the famous build once, run anywhere motto. How does that translate to the sometimes messy world of FPGAs?
Well, Docker's inherent portability, often summarized as build once, run anywhere, directly eradicates that it works on my machine nightmare.
Okay, goodness.
Once we've meticulously built that specific Vivado environment into an image, it's guaranteed to behave identically, whether it's running on your laptop or a beefy build server in the data center or some cloud instance.
Because all the dependencies are inside.
Exactly. The container encapsulates everything it needs. It's guaranteed to run the same everywhere.
That sounds incredibly liberating for teams. I mean, imagine eliminating the setup headaches for new team members. Instead of days of frustrated installation and debugging, it's just a Docker pull command.
It radically simplifies onboarding, yes. And critically, it guarantees build reproducibility and consistency across your entire organization. Fewer coffee-fueled debugging sessions chasing ghost errors.
More time designing hardware.
That's the goal. A trade-off I think most engineers would happily make.
Definitely. And finally, lightweight virtualization. How do containers stack up against traditional VMs? Because VMs have also been used for isolation, right?
They have, yes. And while containers provide a similar level of isolation to traditional virtual machines, they do so with significantly greater efficiency.
How so?
A VM bundles a full guest operating system, including its own kernel. That consumes substantial memory, disk space, and it's relatively slow to start up.
Right.
In stark contrast, all containers running on a single host machine share the host's operating system kernel.
So they're much more lightweight.
Far more. They use drastically less memory, they start and stop almost instantly, and you can pack many more of them much more densely onto a single host server.
Okay.
This efficiency means minimal overhead locally on a developer's machine. And maybe more importantly, in a CI/CD environment, a single powerful build server can run multiple parallel build jobs simultaneously, each in its own clean, isolated container, without that crushing resource penalty you'd get with full VMs.
So faster builds, cheaper infrastructure.
Exactly. It makes the development and testing cycle faster and significantly more cost-effective. It's about getting the most bang for your buck in terms of computational resources.
Okay, so we've established why Docker is such a compelling solution. Now comes the million-dollar question for many listeners.
Yeah.
How do you actually do this? Let's get into the nitty-gritty, the practicalities of architecting this Dockerized Vivado workflow.
Right. The Docker file is your cornerstone here. It's essentially a text-based script that builds the Vivado image layer by layer.
Okay.
You typically start with a minimal base Linux image, like ubuntu.tunubot04, just to keep the final image size down from the start.
Makes sense.
Then you use RUN instructions within the Docker file to install Vivado's numerous system library dependencies using the package manager like apt-get. These are things like build essential, libtinfo5, limcurses5, and various 32-bit compatibility libraries that Vivado, even the 64-bit version, still needs to run.
And the Vivado installer itself, it's a huge, right?
Yeah.
30, 50, even 70 gigabytes.
Yeah.
How do you handle that within a Docker file? You can't just copy it in, can you?
Absolutely not. That would create an enormous, impractical initial layer in your image. The standard approach is actually to host the Vivado installer somewhere accessible on your network, like a local web server that the Docker build environment can reach.
Ah, okay.
Then the Docker file uses a command like regget or curl to download that installer during the build process.
Clever.
And crucially, the installation itself must be completely headless. You have to leverage the installer's batch mode capability.
Oh, clicking next, next, finish.
No GUI involved at all during the build. This typically involves first generating an install.config.txt file, which lets you specify exactly which components and devices you want to install, which is another way to reduce size. And then running the installer executable with flags like batch install and config pointing to that file. You also need to handle accepting the ULAs via command line flags, and for the web installers, securely provide your AMD.com credentials, perhaps through build arguments. It's a complex, multi-step dance to automate this properly.
Wow, that really shows the nitty-gritty involved in taming these massive tools inside a container. What about user setup inside the container? Do you run as root?
No, definitely not recommended. For security and best practices, it's advisable to create a dedicated non-root user inside the container. Let's call it Vivado or something.
Okay.
And you configure things so that all the Vivado operations run as this user. You'll also typically configure that users.bash archi or equivalent profile script to automatically source the main Vivado setting 64.esh script upon login. That just ensures the Vivado binaries are always in the path when you're inside the container.
Got it. But even with all that careful setup, a naive Docker file could easily result in a 200+ GB image, which is, frankly, impractical for distribution or storage. How do you manage that enormous footprint? That seems like a major hurdle.
Oh, image optimization isn't just optional here, it's absolutely critical. The single most effective technique is using multi-stage builds.
Multi-stage builds, how does that work?
You define an initial stage in your Docker file, let's call it the builder stage. This is where you do the heavy lifting, download the installer, run the installation. It might get huge temporarily.
Okay.
Then you define a separate second final stage. This stage starts from a clean base image again, but crucially, it uses the copy Y from builder instruction to copy only the necessary installed toolchain directories from that temporary builder state.
So you discard all the intermediate installation junk.
Exactly. You discard the installer itself, the temporary build files, everything except the final installed product. This alone can often reduce the image size by over 50%, maybe getting you down to a more manageable, though still large, 80 to 100 gigabit range.
That's a huge reduction. What else helps shrink these images down?
Well, within each stage, you need to be meticulous about minimizing layers. And crucially, clean up artifacts within the same RUN instruction where you created them.
Oh.
For example, if you use apt-get install, you should chain it together with apt-get clean and arm-rf varlib lists in the same RUN command. This prevents the package cache and temporary files from being permanently baked into a separate image layer history.
Got it. One command, multiple actions, then cleanup.
Right. Also, always use a dockerignore file, just like you use a .jitignore. This prevents unnecessary local files or directories from being accidentally sent to the Docker daemon during the build context upload, which can bloat your intermediate layers unexpectedly.
Good tip. And I heard there's an advanced technique for dealing with those really large layers, even after multi-stage builds, to improve network performance.
Yes, that's a more advanced optimization. Even after multi-stage builds, the core Vivado installation might still form one single massive layer, maybe 80 GB itself. This can really bottleneck network performance when you push and pull the image.
Right.
An advanced technique involves programmatically splitting this massive directory structure into multiple smaller layers. Think of it like breaking one giant download into maybe 20 smaller simultaneous downloads.
Okay.
A script can analyze the installed Vivado directory, maybe categorize subdirectories by size, and then generate a new Docker file snippet with multiple copy-y from builder commands. Each command copies just a small chunk, maybe a few gigabytes of the installation, into a separate layer in the final image.
So Docker can pull those smaller layers in parallel.
Exactly. Docker's registry protocol and client are designed to handle parallel layer downloads. So splitting that one huge layer into many smaller ones can significantly improve the effective transfer speed, making those 800 gigabyte images far more manageable in practice, especially over slower networks. It's all about efficiency and practicality, how to make this large solution actually usable.
Fascinating. Okay, next hurdle. Licensing. Always critical for specialized software like this.
Yeah.
How does Vivado licensing work within a container, given that it's isolated?
Right, Vivado simply won't run without a valid license. For teams, the most common and flexible approach is using floating licenses. This involves a central license server on your network.
Right.
The container just needs to be told how to contact that server. You do this by setting the ISLNX license file environment variable when you run the container using the E flag. Something like ENX license file 2100 at my-license-server.company.com.
And that's portable.
Highly portable, yes. As long as the container can reach that license server address over the network, it works.
What about node-locked licenses? For individual users who might have a license file tied to their specific machine's MBILIC address or something.
That's a bit trickier. For node-locked licenses, the actual license file, .bilitic file, from the host machine must be mounted into the container using a Docker volume mount. That's the ACWD flag.
Okay.
Then the XNSD license file environment variable inside the container needs to be set to point to the path where you mounted that file, like -v path on hostmylicense.octus.opt license semilicense.ook-e xeisland nxd license file up license semilicense.ilic.
So it works, but it's less portable.
Exactly. It couples that container instance to the specific host machine where the license file is valid and mounted from. Less flexible, for sure.
Okay, licenses are manageable. But now, the big one. How do you interface with physical FPGA hardware, like JTAG programmers or USB debuggers, from inside this isolated container? That sounds like it fundamentally breaks the whole isolation concept.
It does, by design. Granting the container access to physical hardware necessarily means punching a controlled hole in that isolation barrier.
So how do you do it? On Linux, say?
On a Linux host, the most secure and recommended method is to pass specific device files directly into the container using the device flag when you run it.
For example.
Like device debbizzes b0001000.debbiz b001002 to pass just one specific USB device through. Or you could pass the entire USB bus, maybe device debbiz b.debbiz b of USB, if you need more flexibility but slightly less granularity.
They're an easier, less secure way.
Yes, you can run the container with the privilege flag. This essentially gives the container root-like access to all host devices. It's simpler, but it significantly sacrifices the security benefits you gain from containerization in the first place. Use with caution.
Okay. What about Windows hosts, or more likely Windows with WSL, which many engineers still use? That sounds even more complicated.
It is a bit more involved, yes. On Windows, where Docker typically runs within the Windows subsystem for Linux, or WSL2, you need an intermediary tool. Microsoft provides one called uspipt-win.
Okay.
You first use uspipt-list in PowerShell or command prompt to identify the BUSID of the USB device you want to share. Then you use uspipt-bind-bizid BUSID to make that device available for sharing from the Windows host side.
Right.
Then you use uspipt attach for bizid BUSID to actually connect or forward that device into your running WSL instance.
And once it's in WSL?
Once it appears in WSL's dev file system, you can then pass it into your Docker container running within WSL using the exact same device flags as you would on a native Linux host. So it's a multi-step process. Windows to WSL, then WSL to Docker.
Huge. So it's definitely a direct trade-off between that perfect isolation for security and build reproducibility and the practical convenience of interacting with physical hardware for debugging or programming.
Absolutely.
But this clearly shows you how to bridge that gap, how to connect the isolated virtual environment to the physical world when you need to.
And this actually brings us to a really powerful concept, the hybrid workflow. It's about designing your Docker setup to support both GUI-based interactive use and headless scripted operation from the exact same container image.
Okay, so headless mode. That's primarily for automation, CI/CD pipelines, running build scripts.
Exactly. This is the primary use case for automation. Vivado is invoked in a non-interactive bash mode, typically using something like Vivado mode batch source your build script.tcl.
Right.
It's fast, efficient, perfectly reproducible for automated builds. The container starts, executes the script, generates a bit stream and reports, and then exits cleanly. Ideal for CI.
But the Vivado GI, let's be honest, it's absolutely indispensable sometimes for interactive debugging, analyzing timing reports visually, exploring IP configurations.
Absolutely. You need the DUI sometimes.
So how do you get a graphical interface from inside an isolated container?
That's typically achieved using X11 forwarding, assuming your host machine is running an X server, which is standard on Linux desktops and available on macOS and Windows too.
Okay, X11 forwarding. How does that work with Docker?
You launch the container with specific Docker run flags. You need to share the host's X11 socket file by mounting it as a volume, typically xv.tmp.x11-unix.tmp.x11unix. And you need to pass the host's display environment variable into the container, like AE display.
And that tells the GUI apps inside the container
to send their drawing commands back to your host machine's display server. So the Vivado GUI window just pops up on your regular desktop, but the application itself is running entirely inside the container.
Are there alternatives?
VNC is an alternative, setting up a VNC server inside the container. But it generally has worse performance, can feel a bit laggy, and is more complex to set up than X11 forwarding if your host already has an X server.
So this headless first, EUI on demand paradigm, that sounds incredibly powerful.
It really is.
It means developers can primarily build their designs headless for speed, consistency, and automation. But if a build fails, or they need to debug something specific,
they can instantly launch the exact same container image, the one that failed the build, but this time in GUI mode using X11 forwarding. They can then poke around, debug the failed run using all the familiar graphical tools, knowing they're in the identical environment.
That's fantastic.
Yeah.
It means you really don't have to choose between automation and interactive debugging. You get the best of both worlds from one consistent image.
Precisely.
Okay, so with this robust technical foundation now in place, let's talk about the truly transformative applications that get unlocked by having this containerized Vivado environment. These aren't just neat technical tricks. They really start to address high-level engineering and even business challenges.
For me, the most compelling application, maybe the gold standard, if you will, is enabling true continuous integration and continuous delivery, or CI/CD, for FPGA.
Bring DevOps to hardware.
Exactly. This is essentially bringing those automated, rigorous software DevOps practices where code changes are continuously built, tested, maybe even deployed directly into the hardware development lifecycle.
So walk us through that workflow. What does it look like in practice for an FPGA project?
Okay. Imagine a typical CI pipeline, maybe orchestrated by a server like Jenkins, GitLab CI, GitHub Actions, whatever tool you use. It starts when a developer pushes a code change, VHDL, Verilog, TCL scripts to your Git repository.
Right.
This push automatically triggers a pipeline job. The CI runner, the agent that does the work, first pulls the specific tagged Vivado Docker image needed for this project, say, my company Vivado.Trieros 22.2, ensuring a pristine, known good, consistent environment every single time.
No variations.
No variations. The runner then starts the container, checks out the latest source code from the commit that triggered the build, and executes the main build script, usually that TCL script running Vivado in batch mode.
And then, can it run automated tests within that container too?
Absolutely. That's a key part. After the build, the pipeline can automatically run various tests. This could include code linting, running behavioral simulations using tools like vUnit or QuestaSim, if licensed and included in the image, maybe even running formal verification tools, all executing within that perfectly consistent containerized environment.
Okay.
Upon successful completion of the build and tests, critical output artifacts, the final bitstream file, timing reports, power reports, design checkpoints are archived by the CI system and, crucially, linked directly back to the specific Git commit that produced them.
The value here sounds immense. Every single commit is built and validated automatically. You get rapid feedback, you catch integration issues or regressions super early.
Before they become massive, expensive problems found weeks later during manual testing. It creates a reliable, repeatable, and fully auditable trail right from the source code commit to the final verified bit stream. This is just invaluable for quality assurance, for compliance in regulated industries, and ultimately for your team's confidence and peace of mind. This is truly where that initial setup effort for Docker pays off big time. It fundamentally transforms how hardware is developed and verified.
And how does this approach help unify team-based development?
Yeah.
I can imagine that it works on my machine becomes less of a team sport problem.
Exactly. For teams with multiple engineers, having a versioned Vivado Docker image stored in a shared private registry, like Docker Hub, Artifactory, GitLab registry, becomes the single source of truth for the build environment.
Okay.
Onboarding a new engineer, it's reduced to potentially just 2 commands: Docker login to authenticate to your registry, and Docker pull my-company vivado.latest-stable. That replaces potentially days of manual setup, chasing down the correct tool versions and patches, debugging obscure installation errors.
Oh, a pain.
Right. This completely eliminates a whole class of works on my machine problems across the team. It fosters much better collaboration because everyone is guaranteed to be using the identical environment. People can focus on design challenges, not fighting the tools. It's a direct solution to those common team frustrations and inconsistencies.
That makes perfect sense. And what about projects with very long life cycles? FPGAs often end up in products that need support for many years, sometimes outlasting even the official tool support from AMD. How does Docker help manage that?
Docker provides a really powerful mechanism for managing this through version environments. The strategy is for teams to build and meticulously tag Docker images for each specific Vivado version they use in a production project. For instance, my-company vivado.2021.2, my-company vivado.2023.1, and so on.
And store these indefinitely.
Yes, store them securely, perhaps indefinitely in a private container registry. Then each project's source code repository and its CI pipeline configuration explicitly reference the specific image tag that project was developed and released against.
Okay, what are the advantages of doing that beyond just keeping track?
Well, first, it allows for true parallel development. Your team can work on a brand new project using Vivado 2024.1 in one container while simultaneously maintaining a legacy product that requires Vivado 2019.2 in another container, all on the same machines without any toolchain conflicts or complex manual environment switching.
Nice.
Second, for long-term maintenance, imagine a critical bug fix is needed for a product you shipped 5 years ago. The team can simply pull the exact archived Docker image, say my company Vivado.2019.2 product XV1.0, from the registry. This instantly replicates the original build environment with perfect fidelity.
Bit for bit.
Guaranteeing bit-for-bit replication of the original build process and hopefully the resulting bit stream. This is absolutely critical for regulated fields like aerospace, medical devices, or defense, where revalidation is extremely costly or complex.
And for upgrades.
It makes upgrades much lower risk. Teams can start migrating a project to a new Vivado version in an isolated development branch. The CI pipeline for that branch would use the new Vivado Docker image tag. Automated builds will quickly identify any incompatibilities, script errors, IP upgrade issues, timing failures in a controlled manner without disrupting the main development branch or ongoing production support.
So the toolchain itself basically shifts from being this volatile, machine-specific installation that everyone dreads touching
Exactly.
to becoming a stable, version-controlled, and archivable asset, just like your source code.
Precisely. It becomes part of the project's history and assets. This is all about future-proofing your work and ensuring long-term maintainability for these complex, often high-stakes projects.
Okay, let's try to bring this all together then. We've covered a lot of ground, from the deep-seated problems to the technical solutions and the high-level benefits.
To summarize, I'd say the adoption of a Docker-based workflow for AMD Vivado represents a really significant paradigm shift. It's not just a minor tweak. It requires a substantial upfront investment in learning Docker itself, Linux fundamentals, scripting, and in the initial setup effort, especially getting those Docker files right and optimizing the images. But it offers profound long-term benefits in efficiency, quality, and predictability.
So let's quickly recap the primary benefits versus the challenges, just to give our listener that balanced view of what it really takes.
Sure. The primary benefits, as we've discussed, are really unparalleled build reproducibility. The enablement of robust CI/CD pipelines truly streamline collaboration across teams, much simplified toolchain version management, and that invaluable long-term archivability of your complete build environments. That's the payoff.
And the hurdles.
The primary challenges realistically do include that high initial complexity. You need people with expertise in Docker, Linux system administration, and TCL scripting. The Vivado images, even optimized, are enormous, typically 80 to 100 plus GB, which has significant network bandwidth and storage implications for your infrastructure. License configuration, as we saw, can be a hurdle depending on your license type. And interfacing with physical hardware and getting the GUI to work smoothly requires specific, sometimes intricate configurations, especially if you're on Windows or WSL hosts. It's important to have a clear-eyed view of what you gain and what it genuinely takes to get there.
Absolutely. So, given these trade-offs, for whom is this approach most strongly recommended? Who should really be leaning into this right now?
We'd strongly recommend this for teams of, say, 2 or more engineers working together. If you have projects with long maintenance life cycles, or if you're developing designs for regulated or high reliability industries where that reproducibility and audit trail are paramount, this is absolutely for you.
Okay.
Also, if your organization is already committed to modern DevOps practices for software, extending those principles to hardware with Docker makes perfect sense.
Who might not need this, at least not yet.
Well, perhaps a solo developer working on very short-term projects or prototypes might find the initial setup overhead outweighs the immediate benefits for them. The calculus changes with team size and project longevity.
And you mentioned earlier, there's a really critical prerequisite to truly unlock Docker's full power here, isn't there? You can't just containerize any old Vivado workflow and expect magic.
Absolutely not. That's a key takeaway. The full power of Docker for Vivado is only unlocked when it's paired with a TCL-based non-project mode workflow.
Why is that combination so crucial?
Trying to use Docker just to containerize a traditional GUI-driven project mode workflow, well, it would solve the environmental consistency problem, which is good, but it would leave the fundamental version control nightmares and the automation challenges largely unaddressed. You'd have a consistent mess, maybe. The truly transformative approach is the synergy between the two. A stable, predictable, containerized environment provided by Docker, combined with a clean, scriptable, version-controllable, non-project design flow defined in TCL. The container provides the reliable foundation, and the TCL scripts provide the automation and the clean version control interface. It's the combination that turns this into a genuine game changer.
So while the investment is substantial, and it definitely requires a shift away from perhaps comfortable GUI-centric habits for some, it really transforms FPGA development from what can sometimes feel like that fragile artisanal craft into a modern, disciplined, and much more predictable engineering practice. This really serves as your roadmap, listener, for deciding if and how to embrace this powerful methodology.
Indeed. It's not just a technical trick for running Vivado. It's really a strategic evolution that transforms FPGA development into a more predictable, scalable, and ultimately more confident engineering endeavor.
What's fascinating here, stepping back, is how solving this problem of environmental stability fundamentally changes how an entire engineering discipline can operate more effectively. It really raises an important question for you, our listener, to maybe ponder. What other traditionally fragile art disciplines out there, maybe in engineering, maybe even beyond, could be fundamentally transformed by adopting similar principles? Principles of environmental stability, rigorous versioning, comprehensive automation. How might such shifts change the very nature of innovation and problem solving in those fields?